Recording in progress.
Hi, everybody. My name is Christine Maceo, and I'm coming to you from the United States Naval Academy Center for STEM Education and Outreach. And I'm here today to help you with a high school educator workshop, virtual workshop. And today we will be talking about pendulums. So before I get started, I want to thank the Air Force for inviting me here to participate in this workshop with you today. And I also want to acknowledge our sponsors that include the Department of Defense STEM Office, the Office of Naval Research, and the Naval Academy Foundation, and they support the programs at the United States Naval Academy. So I am going to just change the spotlight for a second so that you can see the supplies that we will be using today. So if you look over here, we'll be using a ruler, some tape, a calculator. I will be using a scale. I did not include it on the supply list for you, so we'll talk about that a little bit later, but I'll show you how you could use a scale with this. Some weights, so these are just some hex nuts of different sizes, actually 2 of the same size and 1 a different size. Some scissors, some pencils, and I can't remember if I said some thread. And so those are the supplies that we will be using today in order to study pendulums, and we will also be doing an experiment with pendulums too. So let me clear up the supplies. And of course, I always have to bring it back to math. So the very first thing I want to show you is a chart that looks like this. So one of the reasons I decided to talk about pendulums today is because of the oscillations that you see with pendulums. So an oscillation is any kind of repeated motion or motion that repeats itself. And probably the most common one that you think of when you think about periodic motion or oscillations is a sine wave. So that's exactly what I sketched out here. This is just a sine wave. It's a simple sine wave. It has an amplitude of 1, and what that means is it gets to a maximum value of 1 on the y-axis, and actually it gets to a minimum value of -1 on the y-axis of this axis as well. And if you take a look at this, I told you that it repeats. I actually have 3 cycles or 3 full complete sine waves in this diagram. I get 1 full complete cycle in 6 units, whatever that happens to be on the bottom scale, in 6 units over here. So in these 3 complete cycles, I actually have a total of 18 units on my x-axis or my scale here. This is also called periodic motion when it repeats itself like this. And when the periodic motion is a sine wave like I have here, we call it simple harmonic motion. And simple harmonic motion has a lot of applications in daily life, both in nature and in man-made phenomena. And we're going to use a pendulum today to take a look at that motion. Okay. So before we can study a pendulum, you actually have to build a pendulum. So that's what we're going to do first. And what I would like you to do is take out one of the hex nuts or one of the weights that you gathered for tonight's event or today's event. Actually, I'm in Annapolis, Maryland, so for me, it's nighttime. And some thread. And the first thing we're going to do is just pull out a length of that thread. So I would say about a 1/2 foot. It doesn't have to be exact. We're going to pull out a certain length of thread, and we're just going to cut that. So mine is about 8 inches long, 6 inches long, 8 inches long. And in order to start creating our pendulum, we are going to tie this piece of thread to the hex nut. And I know it's not easy to do, especially with the thread, but if I can do it, you can do it, because it gets stuck to my fingers all the time. All right. And so with the one I wanted you to tie it to, I picked my biggest one, which is the one I have 2 of. So if you could tie it to your biggest one as well. So like this. And I'll give you a minute to finish with that. So the reason that I asked you to get thread instead of something like yarn is that we are going to make a simple pendulum today. And when we make a simple pendulum, the calculations that we do assume that the weight is much, much, much heavier than the string that it's attached to. So we actually consider a simple pendulum to have a massless string. That's the assumption with it. So if you use a thicker string, some of your measurements might be off. All right, and then the only other thing you have to do right now is get out a pencil. And I'm not going to make you tie it this time because you can actually tape it. But if you just kind of wrap that string around the pencil a couple of times and tape it, then what you have over here, and pin the other diagram. What you have is a simple pendulum. So you need to attach this to something. And so you can attach it to the desk that you're working at, or to something like a shoebox. So I actually have it attached over here to the shoebox, and I'm going to bring that up so that you can see it. So I'll give you a minute to tape it to the table and to make sure that it hangs down. So when you do tape it to the table, you want to make sure that the pencil hangs out a little bit so that when you start to swing this pendulum, it can move freely and it doesn't bang into you. And again, I'll just give you a minute for you to attach that to something. All right. So the first thing I want to do is just say one more time that the reason I asked you to pick something that was very heavy in order to make your pendulum is that we are looking specifically at a simple pendulum. And a simple pendulum assumes a massless string and something called a bob. So for in my case, I am using this hex nut as a bob, but maybe you have a washer or something like that. So the other assumptions that we're going to make with this pendulum is that when we pull it off to the side and start to watch its motion, that we actually pull it not too far up. So we're not going to pull it all the way up here. All of our calculations are going to assume a very small angle. And you can practice just letting it go and watching the oscillations or the oscillatory motion, and that's what we're going to study today. Okay, so we are going to take a look at that motion, and at the same time, we're going to fill out a data sheet. So we're going to actually measure and analyze this motion by taking measurements, and we're going to fill out a data sheet. So I am going to repin this over here so that you can see what the data sheet looks like and the kind of information that we're going to measure today. So first of all, we are going to calculate the mass, or we're going to measure the mass of the bob. We're also going to measure the length of the string. And then we're going to start looking at something called frequencies, or the number of cycles in a certain number of seconds. So what I decided to do was count the number of cycles in 5 seconds. And we're going to take that measurement for the pendulum that we just set up here. So actually, that's what we're going to measure first. We're going to count the number of cycles in 5 seconds, and we're going to record it for the pendulum that we just built over here. All right. So I'm going to pull my pendulum just a few degrees over to the side, and I'm going to let it go. And I have a watch on. I'm going to use the time for 5 seconds, and I'm going to count the number of times this moves back and forth in 5 seconds. 1, 2. All right, I counted 5.5. So I'm going to go over here and write down that my pendulum has oscillated 5.5 cycles in 5 seconds. Now, I'm going to take out my scale, turn it on, make sure it's in grams, and I'm going to weigh my pendulum or my bob, and I get about 12.3 grams. So I'm going to put that down right here, 12.3 grams. Then what I'm going to do, come back over here, is I'm going to measure the length of my string. So for that, I just have a ruler. I'm going to turn it to the side, and I'm going to measure the length of my string and turn it this way so I can get it down. And when I did that, I got that my pendulum was 8.5 inches long. All right, so we're just going to leave it like that right now. I'm going to leave the rest of the data table not filled out because we'll analyze the rest of this later. Before I move any further, I wanted to check and see if anybody has any questions or comments about what we're doing right now, because we're about to build another pendulum, and I want to make sure I answer any questions before we move forward. Anybody have any data they want to share? Okay, so I guess everything's going well. What we're going to do is we are going to move the data aside, and we're going to build another pendulum. So I'm going to come back over here. And this time, so I'm going to take out the bob or the nut that I asked you to get as part of the supply. So this is the smaller one as compared to this larger one. So you can see that this one is much smaller. And we're going to redo or remake a pendulum. So don't dismantle the one you made. We're going to make it on another pencil. But we're going to follow the same procedure. We're going to pull out a length of string, about the same as last time. And then we're going to tie the string or the thread to this weight. And again, if I can do it, I know you can do it, because this is, for me, the hardest part of this whole thing is tying the thread to the nut. And I have it like this. So I said last time that my pendulum was 8.5 inches long, and I want this to be the same length. So I'm going to go just a little bit longer than 8 inches long this time and cut it. So that when I tie it to my pencil, I can make it 8.5 inches long. So we've got another bob. It's smaller than the first bob. It's got the same length string. And I'm going to get a pencil and just do the same thing I did last time, which is to kind of twist. Making sure that that string length is about 8.5 inches long. And then I go here. Another bob, another pendulum, and I can do the same kind of analysis that I just did on it. So before I do that, since we're doing an experiment, what I want is to see if anybody who's watching has a hypothesis about what's going to happen when I change the size of the pendulum bob. How do you think this will react? How do you think the period of this or the measurements that we take will change now that we've changed the size of the bob? Before we do the experiment, let's make a hypothesis. You could put it in the chat. Let me know what you think will happen. Keeping the length of the string the same and the size of the bob different. Anybody? All right. Well, I didn't get any answers, so we're going to have to just do this experiment together and see what happens. So again, you can tape your new pendulum to a table, to a desk that you're working on. You can put it on some kind of stand like this shoebox over here, but you want to attach it securely so that the pencil doesn't move and so that the only thing that's moving is the bob itself. All right, so we're going to take the same data that we took with the first pendulum we made. And again, remember, we did not change the string length. What we did was we changed the mass of the bob down here. So this is the smaller bob. We're going to, this bob though is still much, much, much heavier than the thread I used to attach it. So we're still going to consider this thread massless, and we can still consider this a simple pendulum, which means that the only thing that is having this harmonic motion is this bob down here. We're also going to follow the same procedure we did last time, where we did not pull it a large angle, but instead we pulled it a small angle to the side. And we're going to take the same data, which last time what we did was we counted the number of cycles in 5 seconds. So I'm taking a look at my watch again, and I let the bob go. And again, I got 5.5. So I'm going to pull back to our data sheet. And I'm going to record that data. So what I got was another 5.5 cycles in 5 seconds. I kept the length of the string the same at 8.5 inches. So what I'm missing here is the mass of the smaller bob. So I'm going to pull my scale back out again. Turn it back on because it turned itself off. Make sure I'm in grams. And then I'm going to weigh the smaller ball. And if you take a look at that, this is 4.7 grams. So let's take a look at the data that we've taken so far. And what we see is that when we had a 12.3 gram bob on an 8.5-inch string, it cycled 5.5 times in 5 seconds, or oscillated, moved back and forth 5.5 times in 5 seconds. Keeping everything else the same, meaning the length of the string, because that's the only other variable with our simple pendulum, and varying the mass. So we reduced the mass from 12.3 grams to 4.7 grams, but we kept the length of the string the same. We also got 5.5 cycles per second. So if we think about this for a minute and we're trying to see, well, what can affect this periodic or oscillatory motion of a pendulum? It looks like mass might not be involved, because when I changed the mass drastically, I got the same results in terms of the number of cycles per second. When I kept the length of the string the same, I got the same number of cycles per second. So this might lead me to think that mass might not have much to do with the period of oscillation, but it might, but the length of the string might. So, but I don't know that. I would have to test that. So I have a new hypothesis based on the data that I've already taken that mass might not be included in that equation. For me to test my new hypothesis, which is that the period of a pendulum depends on the length of the string, I would have to vary the length of the string. What I want to be careful about is that I don't vary the mass. I only want to change one variable at a time when I'm doing an experiment, because I want to make sure I can attribute whatever changes I see to the one thing that changed. So I happen to bring, and I asked you to bring 2 of the same size nuts or washers or whatever you were bringing for weights. So I happen to bring 2 of the larger ones. So I'm going to use this mass then down here. And I'm going to change the length of the string and take a new reading. So what you want to do is repeat exactly what we did before. You want to take your one remaining nut, which should be the same size as one of the 2 you already measured. And again, mine is the bigger one, so I already wrote that data in. And you want to tie a new string to it that's shorter or longer than the one you did before. So I'm going to do a shorter one because you can't see on my screen if I make a longer one. But you can do whatever you want. But same idea, you're going to tie that string to the nut, and you're going to cut it to a certain length. And then we're going to take that and put it on a pencil. And again, we don't have to tie that again. What we can do is just kind of wrap it and put a piece of tape to hold it. And we get a new pendulum that has either a longer or a shorter string than the one we saw before. And I'll give you a minute to do that. And while you're doing that, I will ask you to use the chat and to let me know if you have any questions about what you're doing right now. I don't see any questions in the chat. Okay, so again, I put my 3rd pendulum now. So this is the 3rd one we've made. I've put it on a box. I attached it to the pencil, and then I taped the pencil to the box. And again, I made sure to push that pencil out a little bit so that when this oscillated, there wasn't any chance of it knocking into the box and interfering with my measurement. So I'll give you another minute to get that tape to your table, to finish doing that, and to tie your string to your nut, and then attach your nut to your pencil, and then attach your pencil to the tape. All right. And again, anytime you have questions, just put it in the chat. I'd be happy to answer it. Happy to answer anything you have, any questions you have about data collection, scientific method, or changing variables. All right, so again, same assumptions. This is a simple pendulum. So we're treating this nut as a bob. We are assuming that the string is massless, and that's why we picked this thin thread to use rather than a large piece of yarn. And for the harmonic motion, for the simple harmonic motion of the pendulum, we do not want to use a large angle. We want to make it really close to vertical here and just move it up a little bit before we release it. Remember, the data that we were collecting, which we will write on our sheet when we're done, was how many cycles does this go in 5 seconds. So I'm going to get my watch in front of me again. Getting ready to release this. Go. And I got 8. So I counted 8 cycles in 5 seconds. Here. We are going to get our pencil. I'm going to record our data here. 8 cycles in 5 seconds. The mass was the same. It was the same type of nut I had for the first one. But what I didn't yet measure was the length of the string. Come back up here. I'm going to turn it to the side. And I'm going to measure the length of the string this time. Start at 1. See? And it is 3.75 inches. So I'll go back to the data sheet. And I've got 3.75 inches here. So these are all the measurements that we were going to take. We measured the mass of each of the bobs, we measured the lengths of each of the strings, and we calculated the number of cycles in 5 seconds. So now we're going to start using some terms that apply to periodic motion or oscillatory motion or harmonic motion, however you want to think about it. The first term we're going to start looking at is frequency. And frequency is the number of cycles per second. So we already measured frequency. We measured 5.5 cycles in 5 seconds. So if I do 5.5 cycles in 5 seconds, that's actually 1.1 cycle per second. So that's my frequency for the first pendulum I made, which was the 12.3 gram mass, the larger mass, and the longer string, 8.5 inches. So 1.1 cycle per second. And you can see why I decided to calculate the number of cycles in 5 seconds. It would be really hard to see 0.1 of a cycle. So it's much easier to calculate down to the cycle per second than to try to count how many cycles there actually were in a second. I got the same measurement with the longer string and the smaller mass. So I don't have to redo the math for that. I just have 1.1 cycle per second. But I will have to figure out what the frequency was for this last one, where I got 8 seconds I'm sorry, 8 cycles in 5 seconds. So now when I calculate this, 8 cycles in 5 seconds. That's why I told you to bring a calculator. You're welcome to use a calculator for this. If I do 8 divided by 5, then I get 1.6 cycles per second. So I've been able to I was able to calculate the frequency of the harmonic motion of each of these 3 pendulums. The other thing that I'm usually interested in when I talk about harmonic motion or sine waves or oscillatory motion or periodic motion is the period. So the period is the number of seconds per cycle. So it's basically the 1 over the frequency, or the frequency upside down. So here for my period for the first one, I would do 5 seconds and I got 5.5 cycles. So my period, or the time it takes for 1 cycle to go, would be, and again, you can use your calculator for this, 5 divided by 5.5 is 0.91. And that's the same for the one underneath, because I had the same frequency, it means I have the same period. For the third pendulum, which was the one with the large mass but the shorter string, when I got a different number of cycles in 5 seconds, I actually do have to recalculate that. And what I have to do is do 5 seconds divided by 8 cycles. And again, you can use your calculator for that. And I get 0.6. So it takes much less time for 1 cycle of the shorter string than for 1 cycle of the longer string. So what does all this mean? So what can we glean from this, and what kind of formula actually ties all of this together? And so you knew I would bring some math in for you. This is a high school educator workshop, so I'm going to bring some trigonometry in and a little bit of physics as well. So we're going to just take a look at a diagram and find out what's going on here. We will develop a formula and we will actually be able to calculate the percent error here. All right. So this is the diagram I wanted to start pointing out to you. So what I have here is basically the top of my shoebox. This is where my pendulum is attached. This is my massless string, which has some length. So either, for me, either 8.5 or 3.75, but right now we're going to call that L. And this is my bob. So this is my pendulum that's going back and forth, and it's actually going back and forth along an arc, and that arc is called S. Now, when we started out, I said that we were going to move some angle away from vertical, but that was going to be a very small angle. So that's marked over here by a theta. And if I look at this little bob over here, there are certain things going on with it. So that it's being held up by tension in the string. So that's one thing that's going on. But it's being pulled down by gravity. And there's a force on it that is the mass times the gravity. So that's the force pulling down on this bob. Now, when I look at this mg here, or this force here, the angle that I moved it up here actually reappears down here. Here's the trigonometry. And I can break this up into 2 components because what I have is a right triangle over here. So I have a cosine of the angle that's adjacent to theta, and then I also have a sine of the angle that's opposite to theta. This is the one I'm interested in because this is the one that's either restoring or righting this pendulum. It's trying to bring it back down around. So this is the force that's acting to move this pendulum along the arc. And it's working to restore it, so I'm going to put a negative sign in front of it. All right, so that's the force that's acting on our pendulum to move it back so that it can start to oscillate back and forth. Now, here's one assumption, and this is why we kept the angle small. There's an assumption that if the theta is small enough, then the sine of the angle and the angle itself are fairly close to each other. So I can make an approximation that this thing over here is actually equal to minus mg theta. So there's the first assumption. That's why when I was pulling that bob, I said I have to make sure not to make the angle too big. All right, so here's that theta over here, and here's the movement of the pendulum along its arc. And if I take a look at this arc length here, then this arc length is actually going to be L. That's the definition of arc length. And this theta then can be written as S over L. So I can rewrite this equation here as mg S over L. What I have, let me just rewrite this for a second, is some constant times some value S, which is a displacement. And this starts to look, and I lost my negative sign right for a second. This starts to look a lot like Hooke's law. This is a high school physics concept where Hooke's law is the force on a spring. It is the spring constant times a displacement. And this actually is known as a gravitational spring constant. So I can use these two pieces of information here together to come up with a way of expressing the period of this motion using the period of a spring, which is T is equal to 2 pi times the mass over K. This is for a spring itself. I'm going to consider this constant over here, this mg over L as the K, and I would get 2 pi times the square root of m over mg over L, or 2 pi times the square root of L over G. That is the period of the pendulum. I have a figure right here. And if you look at that, this is how you calculate, and I just showed you with trigonometry, the period of a pendulum. What's missing in here is the mass. There is no mass. The mass canceled here. So when my results actually make mathematical sense, where the period of the pendulum is not related to the mass, the only thing in here that's not a constant is the length of the string. And that's exactly what we found with our experimental results. And remember, what I did first was I asked you to come up with a hypothesis. We refined the hypothesis. We got these results. We analyzed those a little bit just to kind of make them more readable to us. But then we went back to the physics and looked at the actual formula, the derivation of it, and it matched our results. So what I want to do now is take this formula over here, this 2 pi L over G, and I want to see how close were we really with these period measurements that we got over here. So let me write this down over here. T equals 2 pi square root of L over G. So we're going to use this formula over here, and we're going to see what kind of values we get for the period of each of the three pendulums that we just looked at. All right, so when L was 8.5 inches. Oh, sorry. Yes, when L was 8.5 inches, we can calculate the period for these two together. We can get the period is 2 pi times the square root of 8.5 over G. So G in the English system is 32 feet per second squared. It's normally given in feet. So what we're going to do is multiply it by 12. So we get it in inches because our measurement was in inches. We got 32 times 12. We'll take out our calculator. Look at this. We're going to do 8.5 divided by 32 times 12. Take the square root of that, multiply it by 2, multiply it by pi, and we get 0.94. This is what we measured, 0.91. So pretty close, and we could actually calculate the percent error for that as well. When our length was 3.75 inches, we'll come over to our formula and we'll do 2 pi times the square root of 3.75 over 32 times 12. Get our calculator out. 3.75 divided by 32 times 12. Take the square root of that. Multiply it by 2 and multiply it by pi. And we get 0.62. This is what we got by measuring 0.625. So very close to theoretical. That actually always happens with pendulums. It's really hard to go wrong with. They behave so close to theoretical that if you want an experiment that actually has very little measurement error in it, I mean, this is the way to go for it. Before I go any further, does anybody have any questions or comments about that at all? Anything to discuss in the chat? Okay. I don't think anybody has any questions. So I wanted to point out a couple of other things that are interesting to look at when you start looking at pendulums. And let me pin this. Let me pin my here first. Okay. So this also is a set of pendulums. They also are attached to pencils and attached to a shoebox. They have the same length, string, and they have different sized bobs. Although you really could do this with this observation. We're only going to do an observation here. You could make this observation with same size bobs or different size bobs. So the difference between the pendulums that I looked at before and that I'm showing you now is that these are both attached to the same substrate. So they're both attached to the same box. And I was very careful for the rest of the experiment to attach them to different boxes. And the reason for that is that pendulums actually interfere with each other, or they can affect each other if they're attached to the same substrate like this. So what I'm going to do, I'm not going to lean on the table, is I'm going to take one of these, and it doesn't matter which one, it just happens faster for the bigger one. So I want to make sure you get to see it. And I'm going to do the same thing. I'm going to move it a few degrees, and I'm going to let it go, but I'm going to keep the other one still. And you'll start to see the phenomenon happen right away. So they couple. And they actually couple, they start coupling out of phase, and then eventually they will come in phase together. And that is actually because they're attached to the same substrates. When I started this one going, the substrate itself was vibrating. And this pendulum over here, which has a massless string and a bob at the end, it starts to move in reaction to the vibrations that are in this box being caused by the pendulum that's moving. And so, and they will always couple. And this has been known for hundreds of years that people used to notice it on fireplace mantles, that their clocks would couple. But it actually leads to an important use of pendulums to sense earthquakes. So if you hang a pendulum and the earth starts to vibrate, it will cause a vibration in that pendulum and it can sense an earthquake. So that's a real world application of a pendulum besides the clocks. So that was one phenomenon I wanted to show to you. The other one, notice you might have noticed that there was one part of the data table that we had not filled out yet. And that one actually has to do with a different type of pendulum. So this is also a pendulum. Let me just bring one of my bob ones back up here so you can see the difference. So these are two separate types of pendulums over here. This is the bob one we made with the nut and the thread. This one is a little bit different. This one's made with a rod. And so it behaves differently. This is called a physical pendulum. This one's called a simple pendulum. And if we were to do the same type of experiment with this rod pendulum or physical pendulum, and I know we only have a few minutes left, so I want to do this pretty quickly. We can do the same thing with this. What I did was I took a piece of balsa wood and I just put a piece of straw through it. And this is just a T-pin and it's into a pencil eraser. So I actually have it stuck into the pencil eraser so that it hangs. And it also has a length associated with it, which we can measure in a minute. But I can treat it the same way. So I can pull it a real small angle and I can take measurements on it and see how many cycles per second this has. So I'm going to just give it a second. Hold on, I have to get to an even number here. And then all right, I got 7.5 when I did that. So I will go back to my data sheet here. And I will write 7.5 cycles per second. I weighed it before. It's 5.2 grams. I can make that a little bit bigger. And I know we're running out of time, so I want to write down that I also measured it before and that it's 6.25 inches long. So if I were to take a look at the number of cycles per second here, I have 7.5 cycles in 5 seconds. That's actually 1.5 cycles per second. And if I look at the data that I've taken here, I have 1.5 cycles per second for this rod pendulum, and which was 6.5 inches, 6.25 inches long. And it's almost the same frequency as I got for the really, really short pendulum here. And so I can see here that this probably does not follow the same rules as the bob pendulum that we looked at first. There's got to be something going on in here with it. And that is actually true. There's rotational inertia and rotational motion going on in here. So for a physical pendulum, and you could do the same kind of trigonometric analysis, the formula for the period isn't just L over G, it's 2/3 L over G. So it actually oscillates much more quickly than a similar similarly length, bob pendulum of a similar length. So, and again, that's an extension. You can pull out rotational motion and derive that the same way we derived one over here. All right, I promised I would be done by 7:20 today. So, and it's 7:20 on the dot. Once again, I wanted to open it up to any questions from the chat, any comments from the chat, and see if I can answer some quickly before you head off to your next sessions. Well, thanks to you for coming. I do want to just recap what we did here. We started out with a topic. So I started out telling you that we were going to look at pendulums today. And I didn't tell you much about pendulums other than defining them. I let the experiment lead us toward hypotheses without trying to push you in one way or another. We use the scientific method to do some experimental analysis. And I also only changed one variable at a time as we started to weed out what we were really looking at. I did derive the formula, the math formula, so that we could make some sense of our data. And I based it on some previous knowledge on Hooke's law and trigonometry. So, and then at the end, wrapped everything up together and gave you an extension so that you could go one step further and make this a multi-day lesson in the classroom and extend it to rotational motion as well. So I hope you can find some use for it. I hope that, that you enjoyed your visit. I will be back tomorrow night at the same time, and we will be talking about if statements and computer programming. So I hope to see you there. Thanks, everybody. Have fun this afternoon.